Okay, let's dive into this. There are some really big questions in physics,
Yeah,
right?
absolutely. Huge ones.
And one of them is, where do the really, really heavy elements come from? Like plutonium, for instance.
Yeah, the bottom rows of the periodic table. It's a
Yeah.
puzzle.
And the standard story, it might be missing a pretty, well, explosive chapter, it seems.
That's the exciting part. For years, the go-to explanation involved things like colliding neutron stars. Really dramatic stuff.
Kilonovae.
Right. Exactly, kilonovae. But now, researchers at Los Alamos National Laboratory, they're looking at something else. Another kind of stellar death.
Which is?
Think a really massive star collapsing, maybe triggering a gamma ray burst,
Yeah.
a hypernova. They've got this new theory suggesting these events could be churning out heavy elements, too.
Wow. Okay, so a different kind of cosmic Ford.
Precisely. And we're going deep on this research today. It's exploring, really, some uncharted territory in astrophysics.
We're talking about the final moments of the biggest stars out there.
And the specific paper that sparked this is in the Astrophysical Journal. Let There Be Neutrons. Hadronic photoproduction from a large flux of high-energy photons.
Quite a title.
It is, by Matthew Mumpower and the team. It just came out March 20th, 2025.
So our mission for you listening today is to really get our heads around this new idea, how these gamma ray burst jets might be making heavy elements, and what that could actually mean.
Yeah, the implications are pretty wild if they're right.
Okay, so let's start with the basic puzzle. Why is it so hard to make these heavy elements anyway? Uranium, plutonium?
Well, standard stellar fusion, the kind that powers stars like our sun, it stops around iron.
Huh.
Making things heavier than iron requires a lot of energy and, crucially, neutrons. Lots of them, very quickly.
Right, you need to bombard nuclei with neutrons before they have a chance to decay.
That's the essence of the RI process, the rapid neutron capture process. And yeah, for a long time, as we said, neutron-star mergers seem like the perfect place for that. You get neutrons, you get energy.
But now the focus shifts to these collapsing of massive stars collapsers and the gamma ray bursts they shoot out.
Exactly. Picture this. A huge star runs out of fuel. Its core collapses under gravity. Boom, you get a black hole right at the center.
Doesn't always happen, right? Needs specific conditions.
Right. For these jets to form, the theory suggests you need that brand new black hole to be spinning incredibly fast.
Why the spinning?
It's about general relativity, actually. Frame dragging. The spinning black hole literally drags space-time around with it, twisting up magnetic fields.
Whoa.
Yeah, and it's that twisting, that winding up of magnetic fields that's thought to launch these ultra-powerful jets of plasma out along the rotation axis.
Okay, so the jet fires out, but it's not going through empty space, is it? It's still inside the collapsing star.
Exactly. It has to punch its way out. And as it does, it plows through the star's outer layers, creating this superheated region around the jet itself. They call it a cocoon.
I think I saw a quote comparing it to a freight train through snow.
That was Mumpower, yeah.
Yeah.
Like a freight train plowing through snow.
Okay.
Gives you a sense of the sheer violence and energy involved.
So much power. Okay, but where did the neutrons come in? The standard idea was that neutron stars are, well, made of neutrons. Where are they here?
This is the core of the new idea. They're arguing the neutrons aren't, like, pre-existing in large amounts ready to be used.
They're made on the spot.
Yes. Dynamically produced is the phrase they use. It's the jet itself that creates them.
How?
Inside that jet, you have incredibly high-energy photons, gamma rays. Think of them as particles of light with extreme energy.
Okay.
As these photons blast through the jet and interact with the nuclei of the star's material that gets caught up in the flow, they can actually break those nuclei apart. It's called photodisintegration. And in that process, they can knock protons out or even convert protons into neutrons.
So the jet's photons are literally manufacturing neutrons.
That's the proposal. Mumpower put it nicely. The creation of heavy elements, such as uranium and plutonium, necessitates extreme conditions. We propose a new phenomenon where those neutrons don't pre-exist, but are produced dynamically in the star.
That changes things, because free neutrons, they don't stick around long, do they?
Not at all. About 15 minutes is their average lifespan before they decay.
Which is why you need that rapid capture, the R process, right? Grab them quick.
Exactly. You need a really high density of neutrons available very quickly. That R process is still what we think creates naturally occurring thorium, uranium, plutonium, all those heavyweights.
And this new photon mechanism, it makes them fast enough.
Incredibly fast. Their calculations suggest this photon-nucleus interaction, this neutron creation, can happen on timescales of like a nanosecond.
A billionth of a second.
Yeah, just an unbelievably rapid burst of neutron production right there in the jet.
Okay, wow. So neutrons are made super fast inside the jet, but the R process needs them outside the jet, in the cocoon, right? How do they get there?
Good question. This involves the different properties of protons and neutrons.
Right.
Protons have charge.
Positive charge.
So they get tangled up in the jet's powerful magnetic fields. They're sort of trapped within the jet flow.
But neutrons, no charge.
Exactly. They don't care about the magnetic fields. So as that relativistic jet moving near light speed slams outwards, it acts like a shock wave.
The freight train again?
Pretty much. And this shock wave effectively plows the newly created chargeless neutrons out of the jet and pushes them into that surrounding cocoon material.
Ah, so the jet makes the neutrons and delivers them to the cocoon.
That's the idea. It's a neutron delivery system.
And once they're in the cocoon,
Then you have what you need. You've suddenly injected a huge density of neutrons into this hot, dense stellar material, the perfect kitchen for the hard process.
so that's where the heavy elements get cooked up. In the cocoon, fed by neutrons from the jet.
Precisely. You get rapid neutron capture, building heavier and heavier nuclei, creating all sorts of exotic isotopes. And then, as the whole star is ultimately ripped apart in the explosion.
Those heavy elements are blasted out into space.
Yep, seeded into the galaxy.
It sounds incredibly complicated. You've got gravity, magnetism, nuclear forces, hydrodynamics.
Oh, it is. The researchers stress this is a true multi-physics problem. It involves all four fundamental forces.
Strong and weak nuclear forces for the decays and captures.
Electromagnetism for the jet dynamics, the photons.
And gravity driving the whole collapse and setting the stage, plus fluid dynamics for the jet and cocoon.
And general relativity for the black hole, spin, and frame dragging. It's a convergence of almost everything we know about physics happening in one tiny, violent spot.
And you mentioned earlier some of these isotopes made in the RAR process, we've never actually made them on Earth.
That's right. Many are likely very unstable, very short-lived. So we don't fully know their properties, exact mass, half-life, how they interact. It makes modeling this really challenging.
So what are the researchers doing about that?
They're planning large-scale simulations, trying to model these microphysics interactions in more detail to predict what specific elements and isotopes should be produced and in what amounts.
It's like peering into a cosmic laboratory we can't replicate.
Exactly. Nature is doing experiments under conditions we can only dream of creating. These GRBs might be the only places some forms of matter ever exist, even briefly.
So this isn't just about where plutonium came from. This research could tell us more broadly about how the universe works at its extremes.
Definitely. It touches on really fundamental physics. How do neutrons move through incredibly dense, hot matter? How do these complex systems involving multiple forces evolve?
Are there other applications?
Potentially, yes. Understanding these extreme astrophysical events could feed back into other areas, maybe even national security, in terms of understanding exotic particle reactions, though that's more speculative. But for astrophysics, it's huge.
What about the kilonova connection? You mentioned that. We usually link kilonovae, those optical and infrared glows, to neutron star mergers.
Right. Mergers are still the prime suspect for most kilonovae, but some kilonovae are associated with long-duration gamma ray bursts, the kind that come from collapsers.
Wow, okay.
So this high-energy jet model, by producing heavy radioactive elements in the cocoon, could also explain the glow from those specific kilonovae. The radioactive decay of those newly made elements would heat the ejected material, causing it to glow.
So it offers an alternative engine for some kilonovae.
It does. It's just maybe collapsing stars are another important source for these events, not just mergers. It adds another layer to the story.
That's fascinating, and it connects to something else. Evidence found right here on Earth, doesn't it? In deep-sea sediments.
Yes. This is a really cool link. Scientists have found isotopes like iron-60 and even plutonium-244 in deep-sea crusts and sediments.
And they know it's from space.
The isotopic ratios confirm it's extraterrestrial. It didn't form our solar system. It's residue from some nearby cosmic event, maybe millions of years ago.
But what event?
That's been the mystery. Was it a supernova? A neutron star merger? This collapsor jet scenario now presents itself as another possible culprit, a potential source for that plutonium found at the bottom of the ocean.
So this theory could solve both the origin of heavy elements and the source of these specific space dust particles on Earth.
It's a very compelling possibility. It ties together these different cosmic puzzles.
Okay, so let's wrap this up. The big takeaway is We might have a whole new way the universe makes its heaviest atoms.
Yeah, inside the death throes of the most massive stars, powered by these incredible jets and, crucially, high-energy photons making neutrons on the fly.
It's a fundamental shift from just thinking about neutron-star mergers.
It challenges that picture, or at least adds a major new component to it. And it might explain some of those kilonova glows and, yeah, even that dusting of plutonium on the seabed. The key innovation is really that dynamic neutron production by photons.
It really makes you think. If stuff like plutonium, which we usually link to, human nuclear reactors or weapons, is actually being forged out there in collapsing stars.
A way we're only just figuring out.
Yeah. What else are we missing? If we can find evidence of that event here on Earth, what other cosmic secrets are waiting in the geological record or just out there to be observed if we look at these extreme events more closely?
It's a fantastic question. It just highlights how much we're still learning about the universe's most powerful events. This work opens up new windows, new questions to ask.
It really shows the universe is, well, constantly surprising us with its violence and its creativity all at once.
Absolutely. The quest to understand these fundamental processes, how everything came to be, it just keeps getting more interesting. There's always another layer to peel back.